Okay, yesterday we talked about the idea of temperature, and temperature is your average kinetic energy of all the molecules there. It started out the ancient theory of temperature was the idea there was a caloric, there was this invisible fluid within entities, and that invisible fluid was what was created that created the change in temperatures of objects. Okay, that was the initial, and that was the only thing they went with, because once again, we related back to how that was developed. I can only guess that was developed by, you know, the idea of what we have in our body is fluids and blood that warm or cool our body. Okay, and they dealt with the same thing here with regards to how objects cool. Okay, we can use an invisible fluid in there that made the objects get warmer or colder. And then you had the average kinetic energy, proportional to the average kinetic energy of the atoms. Once again, it's the average kinetic energy, depends on the size of the, doesn't depend on the size of the object because you're taking the average of it. So that was our kinetic theory of temperature. Thermometer is a device placed in contact with the environment to get equilibrium. Thermal equilibrium is one thing to both achieve the same temperature. Once again, if I would close this door, if we would put 30 people in this room, we would put 30 people in this room, we would close the door, we would put the blinds down, we would put towels underneath the door so there's no air transferring in and out. We are keeping an isolated system, as we've talked about before. And you had 30 people in this room. Okay, if it started out at 70 degrees in here, and you put 30 people or 40 people in this room, after an hour or two, this room would get awful stuffy. The temperature would rise just by all these people being in the bodies, because each one of your bodies is 98.6. So you are placed in an environment that's 72 degrees or 70 degrees, the temperature rises to 75, 76, 77 degrees because the room is trying to achieve your temperature. We're trying to achieve a thermal equilibrium. Okay, a thermometer is placed in contact with something until you get thermal equilibrium. When you take your temperature, you put the thermometer in your mouth, beep, 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 you read the thermometer. Okay?
Okay.
Thermometers are usually filled with mercury. Let's see, freezing point. Talked about freezing point. Degrees are divisions of degrees. Divisions on the thermometer. Basically, they are based on your freezing point of water and your boiling point of water. Okay, Fahrenheit degrees is 32. It's 32.174, but we use 32. 212 point, I can't remember that one. But you have an approximately 180 degrees. When we talk about the Celsius scale, named after Andrew Celsius, sometimes called the centigrade scale, because that goes into your basis of 10. Your degrees from freezing to boiling is 100 degrees, a factor of 10. We can convert from Fahrenheit to degrees, or Fahrenheit to Celsius, Celsius degrees. If I use Fahrenheit is equal to 1.8 degrees Celsius times 32, or plus 32, that would convert us into degrees of Celsius and Celsius to Fahrenheit. Kinetic energy of atoms is positive. If a substance has a negative temperature, the average kinetic energy must be positive. Kinetic energy is a scalar quantity. It's always positive. So how do we deal with average kinetic energy and dealing with negative quantities? Maybe. There we go. Which takes us to William Thomson. Who is sometimes known as Lord Kelvin. Lord Kelvin. He discovered the Kelvin temperature scale. The Kelvin temperature scale, Lord Kelvin, William Thomson. Now, what's significant about this is it takes the negatives out of the world. The negatives with respect to temperature. So we can deal with proportional to the average kinetic energy, and negatives, we don't have to worry about them anymore. When you're working in chemistry, when you work in the chemistry world and you're looking at Boyle's law, Chuck law, ideal gas law, dealt with the idea of temperature, you had to convert your degrees into Kelvin. Okay, if you remember that, you had to convert everything into Kelvin to deal with them. There exists no upper limit to temperature. There exists no upper limit to temperature. The sun's core is 1.5 times 10 to the 7th degrees Celsius. But you have other stars that are even hotter than that. You have no upper limit to temperature. Whenever you say it can't get any hotter than this, it can. Now, the hope is you look at during the summertime, and they do the Weather Channel, and they look at Phoenix, Arizona, and the Death Valley, Arizona, or Death Valley, Nevada, and they look at the temperatures out there, and we have a new record of 120 degrees or 125 degrees. It has never been this hot before in the desert, 125 degrees. You might say, well, that's your upper limit. Well, that might be the upper limit for what we have on the earth. But can it go even further? Yes, it can. But there exists a lower limit. But there is a lower limit to temperature where all subatomic matter stops moving. There is no kinetic energy. This happens at 0 Kelvin. All subatomic matter stops moving. At 0 degrees or 0 Kelvin. When you talk about the temperature scale, Kelvin does not even have degrees to it. It's just Kelvin. It's not 0 degrees Kelvin, it's just 0 Kelvin. Now, you look at this desk here, it is a solid. There's atoms in here that are still vibrating back and forth. Okay? Even though it is a solid fixture, we say, well, it's solid, everything is not moving. There's still subatomic particles that are moving. There's electrons, there's neutrons, okay, that are orbiting atoms. Okay, you have atoms that are here. You have electrons and neutrons that are still orbiting and spinning around there. Okay, and protons. I can't remember. They keep spinning all around there. Okay, when you hit 0 Kelvin, those electrons, neutrons, and protons, they stop moving. They stop spinning around the nucleus. They are just there. That happens at 0 Kelvin. And this happens at negative 273.15 degrees Celsius. At negative 273.15 degrees Celsius, all atoms stop moving, all subatomic particles stop moving. The neutrons, electrons, This is 0 Kelvin. Which is really cold. As gases cool, they contract and reduce in volume. If the gas can remain a gas at 0 Kelvin, then the gas will reduce to 0 volume. Because when you cool a gas, it will liquefy. Okay, gases, vapors go into liquid, and they go into a solid. Okay, so that is the dominoes that fall there. Okay, if you're able to keep a gas and take it down to 0 Kelvin, what will happen is the volume of the gas will reduce down to nothing. There will be no volume there. An example, helium will liquefy at negative 268.8 degrees Celsius, which is 4.35 Kelvin. So helium almost makes it there. And that's at standard pressure. I mean, you can pressurize, you can liquefy helium if you look at your PV equals PV, okay? If you increase your pressure, if you look at Chuck's and Boyle's laws and deal with the ideal gas law, PV equals nRT, you can increase pressure or decrease pressure and increase your volume. You can also look at temperature in that regards too. To change from Kelvin to Celsius to Kelvin, you can take your degrees Celsius, add 273.15 to it, and you'll convert that into Kelvin. So you add 273.15 to Celsius, and you'll get your Kelvin. Kelvin increments are equal to the Celsius increments. These are the same. So your Kelvin increments will equal your Celsius increments. Which will then lead to the idea of your change in temperature, your delta T in Celsius will equal your delta T in Kelvin. Which is nice if you're looking at delta T and you're looking at a change in temperature, which we will be. If you look at your change in temperature in Kelvin, that will also be the same as change in temperature in Celsius, which will help us out because when we start dealing with heat transfer, we use a formula as MC delta T. Our delta T is involved within the problem. And when you look at your C value, these are constants of heat transfer. Those typically, they'll be Kelvin. And you sit there and say, oh, I gotta change from Celsius to Kelvin. Well, if you have it in Kelvin, that's also in Celsius. Okay, you can always convert them in Celsius too. Things.
went nose blind to it after like 5 minutes.
Huh?
I went nose blind to it after like 5 minutes.
It smells like BO.
I'm used to that, to each boy.
When objects are placed in contact with each other, energy is transferred until thermal equilibrium is achieved. Okay, when you put objects, if you would take an ice cube and put it in a glass of water, or you take an ice cube and you bring it into this room, okay, the room and the ice cube will exchange energies back and forth. There will be an area that cools around the ice cube. It will be cool around the ice cube. But then it will transfer out to a different area, and that area will cool. So you have a small area that will cool. But when you cool the ice cube, or when the ice cube loses that coolness, it starts to melt. So you have an interchange between the ice cube and the environment where the temperature of the ice cube will increase and the environment will temperature will decrease. You will exchange this energy back and forth until you achieve thermal equilibrium. Eventually the ice cube will achieve the temperature of this room. You'll get a thermal equilibrium. In an isolated system, thermal energy lost by one object is gained by the objects in the system. So if we isolate the system, once again, if you close the door, stuff towels underneath, all the cracks and everything, and we just isolate this room, we turn off the air conditioner over there, okay, we will try to achieve a thermal equilibrium in here. Ice is dropped into a beaker of water. Thermal energy is lost by the ice cube, or thermal energy is lost by the water and gained by the ice cube. So if we have an ice cube here, we have an ice cube and some water. The temperature of the ice is less than the temperature of the water. So what will happen is we will have an interchange of thermal energies between these objects. Energy that's lost by the water will be gained by the ice cube. So what you'll have is you'll have this thermal energy that is leaving the water and going into the ice cube. And you'll interchange energies until thermal equilibrium has occurred. Okay? The water will cool down, will cool, the ice cube will melt, and it will heat up, and it will melt and turn into water. So you'll have this constant interchange between the ice cube and the water until you achieve a thermal equilibrium. The greater the temperature difference between the two objects, the faster the energy will be transferred. Okay, so you'll have a rate of energy being transferred. If you put an ice cube in you go to your spigot and you get hot water out of your spigot and put it in glass. You fill up a glass of hot water and then you put an ice cube in that water. it will melt faster. If you put ice in a boiling tub of water, it will melt very fast. If you put ice in a glass of water that, if you do the cold water on your spigot, and you put ice in there, it's not gonna melt as fast. So the greater the temperature difference you have, the faster the energy will be transferred. So if you drop ice into a boiling pot, the ice cubes will melt faster. Ice cubes will gain thermal energy faster and then will melt faster. So as you go back and forth, thermal energy will go a little bit faster when there's a greater temperature difference. When you talk about heat, thermal energy, this is the thermal energy that's transferred. Heat is thermal energy that is transferred. Since we are talking about thermal energy, it is energy. And when we talk about energy, when you talk about thermal energy, when you talk about this energy, you're going to be in joules. If you think back to when we were talking about mechanical energy, the conservation of mechanical energy, we have potential energy, we have kinetic energy. That energies are going to be transferred back and forth between potential and kinetic energy. If it's a perfect system, we don't lose anything to thermal energy. But no system is perfect. So we have thermal energy friction that's being put into that. So you have a loss of thermal energy, which is heat, which is also in joules. When you talk about English units, these are in calories. A little bit different than the calorie. It's related to, but not really related to, like if you eat an Arctic squirrel that has 900 calories of fat. Okay? It's somewhat related to, but not really related to the idea of that same calorie. So you have 1 calorie is equal to 4.186 joules. We have thermal conduction. It's warming of a part of an object that is in contact with a heat source. When you talk about thermal conduction, you're in contact with. Okay, you're in contact with the heat source. If you put an ice cube on your hand, that's the idea of conduction. Exchange of energy by direct interaction between molecules of substance in contact and there exists a temperature difference. Once again, think about it if you had an ice cube in your hand. If you put an ice cube in a glass of water. Okay, that is the idea of conduction. Because you're going to change temperature, you're going to have interaction between the molecules. If you put an ice cube in your hand, the area, if you sprain an ankle or you had to ice an ankle or ice a muscle or whatever, you put a bag of ice where you need to. Okay? The rest of your body does not get cold. But if you put it on your wrist, or you put it on your ankle, your ankle will get cold. But if you're putting it on your ankle, your pinky's not going to get cold because you have ice on your ankle. Okay? So when you have conduction, you have direct connection or contact between the objects. But the object where you have the contact is going to change. The part of the object in contact, the warmer the body has molecules with greater kinetic energy, and this is just the theory behind why this happens. The part of the objects in contact, the warmer body has molecules with greater kinetic energy because they are warmer. Okay? This kinetic energy is transferred to the molecules of the cooler body, increases their kinetic energy and the temperature of the cooler body. The outer layer of the atoms will transfer to the inner layer of the molecules. Kinetic energy and temperature are then increasing. So if you think about when you put ice on a certain part of put ice on your ankle, your molecules of your body will be very active. Okay? You're going to cool down your ankle because you've iced it. Those molecules will slow down. Okay, those molecules will slow down, and when they slow down, they'll get colder. But the ice is losing some of that, or is gaining heat from your body. So what is happening with your ice is, if you think about the heat going from your body to your ice, what's happening to the ice is the molecules will start to speed up. They'll increase in kinetic energy. What is darkness? What is if you're going to define darkness, what?
The absence of light.
The absence of light. Okay? Darkness is the absence of light. Well, when you start talking about the thermal aspect of it, cold is the absence of heat. Because when you have something that's cold, the kinetic energy of the objects and the molecules slow down. And when the kinetic energy of the molecules slow down, it loses temperature. Okay, so when you're losing the average kinetic energy, you're losing temperature. So what cold is the absence of kinetic energy, or the absence of heat. So you can think about cold is the absence of heat, which is the absence of kinetic energy. You've lost the molecules, whatever you're cooling down is losing kinetic energy. So when you lose that kinetic energy, you lose heat. Because heat, or temperature, is proportional to the average kinetic energy. So I'm losing kinetic energy, I'm losing temperature, I'm decreasing in temperature. The more dense the material, the faster the object will heat or cool. The more dense the material is, the faster the object will heat or cool. Metal will heat or cool faster than water because it's more dense. And the question is, why do more dense objects heat or cool faster? Well, when you're heating or cooling, you're either increasing or decreasing in your average kinetic energy. Okay, you're increasing or decreasing in average kinetic energy. Your interaction between molecules is your average kinetic energy. Well, when objects are more dense, molecules are closer together. when molecules are closer together, it's easier to have a quicker exchange of energies, kinetic energies. So when you're more dense, you're more packed together, your kinetic energy can transfer faster. And if your kinetic energy can transfer faster, that means it's going to increase in temperature faster or lose temperature faster. Don't suggest this, but if you think about it, you boil water. You have a pot of water, okay? You have a gallon of water you're trying to boil. You put it on the stove, you click it on high, you put it in the pot, you put it on the stove, click it on high, and it turns really red at the bottom. And it takes 5 minutes, 6 minutes, 7 minutes, 10 minutes maybe to boil, go to boiling. Okay? It takes 5 to 10 minutes to get to boiling. Okay? If it is boiling, it's 212 degrees, 100 degrees Celsius. You take a metal spoon and you put a small metal spoon and you put it in the boiling water and you hold on to that metal spoon. After a couple minutes, you're going to have to pull out the spoon or take your hand off the spoon. The reason why, it's only going to take a couple minutes for that spoon to boil, to heat up to 212 degrees, 100 degrees Celsius. The spoon will heat faster than the water that's boiling. Why? Because the molecules are close together and it will transfer heat a lot quicker. Heat conductors, substances that rapidly transfer energy into heats. Transfers energy into heat. Metals. These are heat conductors. Once again, if you're trying to transfer heat, you want to use heat conductors, which are metal. Heat insulators. Substances that slowly transfer heat as heat, transfer its energy as heat. Cardboard, cork, insulation, styrofoam. You go get a hot cup of coffee, okay? If you look at your hot cup of coffee that you get, it's not in a metal container. It's in a paper container, a cardboard container, or a styrofoam container. Reason why? The coffee will stay warmer longer. You go down to the double D down here. Get yourself an Arctic scroll from the double D. Okay? You look at the container that the Arctic scroll's in. What is it? It's a styrofoam container. The reason why is for you to eat that Arctic squirrel, you have to hold it. You have to put it in your hand to hold it. Well, what you have in your hand is 98.6 degrees of thermal energy, or of heat. Your temperature of your hand is 98.6 degrees. If it was in a plastic container, what's going to happen is your ice cream is going to melt very quick. But if you have it in a styrofoam container, you now have a little bit of insulation there that's going to slow the transfer of heat. So it's in a heat insulator. If you take a look at Yetis, okay, In the walls of Yetis, what do you have? I've never taken one apart, but you'll have some insulation in there. That's going to keep your ice, and your cold drink, a cold drink. Okay? So you look at the idea of an insulator, you're trying to insulate, you're trying to keep the separation between the two. Your house, you have an attic, you have walls in your house that are full of insulation. The reason why, if you did not have that insulation there in the wintertime, your house would be really cold. You turn on the furnace and that heat would just be going right outside. Convection. Some of you may have a convection oven. It's conduction of a fluid enhanced by the motion of the fluid. It's conduction of a fluid by a fluid enhanced by the motion of the fluid.
They have some sort of ceramic lining.
Inside of there. Alright.
So that's just actually a barrier to delay the interaction between outside and inside.
Yeah. When you look at convection, a lot of you have you may have a convection oven, okay? Which inside the oven you have a fan. Basically, it blows heat, and it assists in the warming, cooling of the object. Hair dryers. Okay, of course I'm into all my hair dryers. Okay, is the idea of convection. Your hair is going to heat up by a hair dryer. If you have a cold thing of pop, 16-ounce thing of pop, it's in a plastic insulator or in a plastic container, and you hold outside on a windy day, it will warm very quickly. If it's not as windy, it won't warm as quick. The wind blowing enhances the cooling and warming compared to the wind not blowing. So if you have wind that is blowing, it's going to enhance it and make things go a little bit quicker. And then you have the last one, which is electromagnetic radiation. It's a transfer of thermal energy in the form of electromagnetic waves emitted by atomic and subatomic agitation of the surface of a body. It does not need a median. All waves travel at the speed of light. And the example of electromagnetic radiation is the sun. How the sun warms up the body or the earth. And if you're outside in the sun, you are dealing with the electromagnetic radiation of the sun. Right, tomorrow we will come in and we'll start throwing some numbers at you, and we'll start dealing with some problems in regards to heat transfer. The next 2 days we'll deal with heat transfer between molecules or between surfaces.